now at Harvard, talking about astrophysical signatures of dark matter annihilation.
Okay. Hi, I'm Greg Durbler. So today I'm going to be talking about dark matter annihilation and some of the astrophysical signatures of that are potentially observable. So this is a topic that has gained a lot of traction recently, mostly because there's lots of data coming in, lots, if not somewhat controversial. So we'll get into that later. So these are the primary people that I've worked with on these topics: Doug Finkbeiner at CFA, Dan Hooper at Fermilab, and Gabriela Zaharias at Argonne, and then Neil Weiner, Ilias Hollis, and Lisa Goodenough, folks at NYU. Okay, so let me just first start off with a little background. So why do we consider WIMPs and dark matter annihilation at all? Why is this something that we even think of when we think of dark matter? Why are we concerning ourselves with this? Well, I'm not a particle physicist, but I have particle physicist collaborators who you saw on the previous slide. And if you were to ask them what is the simplest possible model of dark matter you can come up with, this is sort of something like what they would answer. They would say, well, let's consider supersymmetry because there's not a lot of room in the standard model left for a dark matter particle. Then in supersymmetry, the simplest possible particle would be the lightest stable SUSY particle, which is also known as the neutralino. Then they would say particle physics-y things like it's its own antiparticle, also known as a Majorana fermion, that it's a linear combination of the Higgsino, the Bino, the Wino, etc. But there's lots of other candidates, of course. So there's a review by Gianfranco Bertone, Dan Hooper, and Joe Silk. 2004 presents a really comprehensive list, so I would highly recommend it. Okay. So this whole idea of WIMPs, and the reason that we consider them at all, is motivated by what's called the WIMP miracle in particle physics. And it goes something like this. So these are not real Feynman diagrams, they're cartoons. So in the early universe, let's say that the dark matter is a thermal relic of the Big Bang. So that means that process I'm going to describe right now. In the early universe, dark matter particles are self-annihilating and going into some kind of fermion and antifermion by some process that we don't know. And there's enough energy in the early universe that these fermions eventually go back to being dark matter particles. So they're in thermal equilibrium. So then as time goes on, the universe cools, and these guys no longer have enough energy to get back to be WIMPs, neutralinos. So eventually the neutralinos are annihilating, but they're not being recreated. And then after a sufficient amount of time, the universe expands to the point where the dark matter particles don't meet each other. And at that point, the particle density freezes out. So this is a plot that I stole from a talk Jonathan Feng gave at Fermilab in 2007, which illustrates these three times. So this is co-moving number density as a function of time. In the early universe, everything's in equilibrium, so the number density stays about constant. As time goes on and the universe cools, the number density of WIMPs drops. And then at some point, the number density of WIMPs freezes out. So this freeze-out density varies as a function of cross-section. Here, sigma A averaged over a thermal velocity distribution. And the bigger that cross-section, so basically the bigger that one WIMP looks to another WIMP as they're coming in towards each other, that changes the relic density. With increasing cross-section, meaning that you have annihilations for longer, so you have a lower relic density. So the WIMP miracle part of this is that it turns out that the relic density in the universe, there's a complete calculation in Youngman et al. 1996. The relic density in the universe is something like 3 times 10 to the minus 27 centimeters cubed per second over the annihilation cross-section. And now the annihilation cross-section, if you consider a weakly interacting particle, is something like 3 times 10 to the minus 26. And so the reason this is a miracle is because if you plug this in here, you get about the right relic density that we see from WMAP or something like it, other cosmological probes. So this is for a neutralino of mass about 100 GeV up to about 1,000 GeV. So the bottom line here is that cosmology alone suggests that potentially we consider weak-scale dark matter. All right. So for the purposes of this talk, basically everything is going to derive from this. So the specific interaction that happens here, we won't care about too much. But basically, two dark matter particles annihilate. Something happens, we don't know what that something is. And in the end, there's electrons and positrons. So the details of what goes on here vary with the specific model vary with your specific supersymmetry model for the WIMP. Okay, so the chi-chi can annihilate to BB bar, W's, Z's, etc., etc. And then, but in the end, everything cascades down, and eventually you have electrons and positrons. And you can construct dark matter models, indeed, that go straight to electrons and positrons, or to mu's, or something. The parameter space is pretty big. So these multiple annihilation channels means that there's a large range of energy distributions for the electrons and positrons that come out theoretically. Okay, and the energies of these guys are in the order of, at least like 50 GeV and on downward, up to a particle mass. By conservation of energy, you can't make electrons with more energy than the mass of the particle. Okay, but the bottom line here is that the injection of these E plus E minus by neutralino annihilations or by WIMP annihilations has astrophysical consequences that may be observable. So those astrophysical consequences are what I'm going to talk about for the rest of my talk. And they basically separate into a couple of different things. So the ones I'm going to focus on is detection of these E plus E minus. Later on in the talk, I'm going to focus on detection of these E plus E minus local to nearby Earth with cosmic ray detectors. But these E plus E minus also interact with the galactic magnetic field and make synchrotron radiation. So the reason I'm talking about synchrotron radiation is because there's an excess of microwaves towards the galactic center, which is potentially consistent with the WIMP annihilation scenario. So in order to actually get there, though, we have to get into the somewhat messy subject of CMB foregrounds, which we'll do for a while here. Okay, so here's basically the idea, the reason that CMB foregrounds connect with dark matter. So WIMP annihilations may produce gamma rays. So when two WIMPs come together, there's a lot of excitement in the field right now about two WIMPs annihilating and producing gamma rays in the process, right? So this is so-called prompt gamma ray annihilation, potentially detectable with Fermi. There's been lots of movement on that topic. But these WIMP annihilations also generically produce E plus E minus, cosmic ray electrons. And the number density in the galactic center is very high, so there's lots of E plus E minus injected. There's a significant magnetic field, and then B field plus many electrons gives you synchrotron radiation, and in 10 to 100 gigahertz may be observable by WMAP. Okay, so here's WMAP, here's the CMB. Of course, when the data comes down from the satellite, it doesn't look like that, it looks like this. And it is all of this galactic interstellar medium emission that we're going to be talking about for the next few minutes, and that we're going to be concerning ourselves with. The CMB, which you can barely see in the projection here, up here, is going to be a nuisance, and actually a pretty significant nuisance, as we'll see in a moment. Okay? All right. So how do you make microwave emissions in the galaxy? There are a handful of ways that are illustrated with this cartoon down on the bottom. So there's synchrotron radiation from electrons which have been shock accelerated by supernovae. So you have supernova go off, shock accelerates electrons, produces synchrotron radiation. As those electrons diffuse throughout the galaxy, they preferentially lose energy at higher energies, and the spectrum softens compared to what the injection spectrum is. So in the WMAP frequency range, so here 10 to about 20 to 94 gigahertz, 23 to 94 gigahertz, the spectrum of synchrotron goes roughly like a power law, something like intensity goes as frequency to the -1. So around here in the WMAP range, there are many competing foregrounds. But down here at low frequencies, since synchrotron is rising with frequency, we have a map at 408 megahertz, the Haslam map from 1982, which basically traces synchrotron emission. It's dominated by synchrotron. And to a lesser extent, there's something called free-free emission. So free-free emission is thermal bremsstrahlung emission when free electrons collide with protons and are accelerated and create this bremsstrahlung emission. So thermal bremsstrahlung is not really dominant at any frequency, so there's no frequency we can go to and get a map of free emission in the sky. So we use H-alpha, an H-alpha map that was assembled by Doug in 2003 from several surveys of H-alpha. And the reason we use H-alpha as a tracer is because these electrons, which are colliding into the protons and giving you free emission, are also recombining with protons. And that H-alpha line is the H-alpha recombination line. There's also dust emission, and dust emission comes in two kinds. Here is illustrated thermal dust emission. So these are dust grains which vibrate in equilibrium with the surrounding radiation field. And as they vibrate, they produce microwaves. So this is dominant at high frequencies. Behaves roughly like a black body, though with a bit of a power law tail down here. And we have a map at these high frequencies at 100 microns. This is the SFD map. So this is the map, that same map at 100 microns, evaluated, extrapolated through this curve down to 94 gigahertz. So the FDS map of 1999. So there's also something which I won't talk about too much throughout the rest of the talk called spinning dust emission, which is when the smallest grains are excited into rotational modes rather than vibrational modes by collision with ions and fluctuations in plasma density, et cetera, et cetera. These very smallest grains have electric dipole moment because they're not spherical. And as they get excited into these rotational modes, they emit spinning dipole radiation. And so that has a very characteristic spectrum. It basically has a bump around 20 to 60 gigahertz, which I haven't shown here, but comes up around here and then falls off. Okay, so this is a cartoon picture of the spectra throughout the WMAP range. But to actually measure those spectra, here's the technique we use. So we do something called template fitting. So template fitting is basically taking a linear combination of templates at different frequencies and fitting them to the WMAP data, minus some estimate for the CMB. So this is going to be important in a second. So then you solve for these coefficients, which is the linear weighting of the templates, which give you the data. And those coefficients represent estimates for the synchrotron, free and dust spectra. But in actuality, they're not, and this is a function of frequency. I've shown the 23 gigahertz data here. But of course, you can do this for each band, and you get an estimate of the spectra. Now, they're not the actual spectra. They're actually the Haslam, H-alpha, and FDS99 correlated spectra. But to the extent that these templates morphologically match the emission in the WMAP bands, they are estimates of the spectra. OK, so here's a mathematical statement of what I just said in words. So we do a multilinear regression template fit in which the bands are completely decoupled. We don't assume anything about the spectrum for each template. So the spectral shapes are unconstrained, but all we assume is that they're constant across the sky. And in fact, we also break the sky up into smaller little regions for some variation across the sky. And then we solve this matrix equation where this P is a matrix of the templates. This A is that vector of SF and D. And W is the data minus the CMB. And then we basically invert this matrix to solve for the coefficients A. So the templates are the Haslam template, the FDS99 dust map, and the H-alpha map assembled from these surveys. And for the CMB, we use 6 different types of CMB estimators. So how do you make a CMB estimator? To make a CMB estimator, you have to take the data, the WMAP data, and get rid of the foregrounds. Right? So there are multiple ways of doing this. The most common is to take a linear combination of the WMAP bands that approximately cancels foregrounds while maintaining a unity response to the CMB. That's actually this guy right here. So as you can see, it does an OK job. It does a pretty good job, especially at high latitudes. It's not the kind of map you want to do cosmology on, or at the very least, you want to exclude a lot of the plane because the map is not very reliable in the plane. But there are other ways that you can make CMB maps. You can remove maps. You can remove foreground emission with templates and say that's my CMB. You can do the whole thing in L space. The details are not important. But the problem is that any CMB map that you make necessarily has some residual foregrounds in it. Right? You can clean the CMB map, but you'll never do perfectly, so you always have some residual foregrounds. So then when you do this process and subtract the CMB off of the WMAP data, you've already contaminated your spectra. So why is that? So these are the 6 CMB estimators we use. They all look identical, but they're not. Each one has a little bit of foregrounds in them. So when you go to solve this equation, your CMB is not actually a CMB. It's the CMB plus a little bit of some of your foregrounds. So here, this is the synchrotron map. So when you go to solve this equation, you can see that your estimate for S over here is going to be biased by this factor. Okay? So each one of your derived coefficients is actually going to be the true coefficient minus the spectrum of the CMB times some bias factor, which you don't know. This is called the CMB cross-correlation bias because it has to do with morphological correlations between the CMB and the foregrounds. But it's unavoidable. And I'll show you some of those effects in a minute. Okay, but here comes the crux of it. So say we take the WMAP data and do this multilinear regression fit to these templates minus the CMB. If these templates are behaving perfectly and tracing all components exactly, then this should just give us noise. And in fact, it doesn't. So there's this fifth foreground, which was termed the haze by Doug Finkbeiner in 2004, which is a roughly spherically symmetric blob towards the galactic center. So this gray spot here is a mask that is masking out regions where there's significant dust contamination.
What do you mean by roughly?
I'm sorry?
Roughly spherical.
So it's not spherical to the extent that it doesn't look spherical.
I guess what I'm asking is that since you have at least some information on it, you can do a power spectrum, for example, to see what the substrate is like.
Sure. So the resolution is such that you couldn't do a fantastic job, but you could take a power spectrum and say what the sort of power looks like. It kind of looks like it has a little bit of elongation down here. It's kind of hard to tell everything going on up here. There's lots and lots of dust contamination up here, and things are very complicated. Sure.
Does the residual, which is really what we're talking about,
Yeah.
does the residual have short distance structure as well as the sort of hazy structure that we were talking about?
So it does not have short distance. It does not have short distance structure like.
You expect that any residual should have a lot of residual on a lot of these scales.
Sure, then that does not seem to be the case. So this is pretty smooth emission, actually, and that's going to be an important point later.
There are other patches in this map.
Yep. Like this guy right here.
I mean, are those, in a meaningful sense, less statistically significant?
So yeah, okay. So here, I spent a lot of time on this region. So this is the Gum Nebula, and there's lots of dust here. Spinning dust is incredibly complicated across the face of this thing. So the template for this is actually a big H alpha feature. The template for H alpha is failing because there's a lot of dust in this region. The temperature is changing a lot, but also this is an incredibly bright region in the sky, actually. And the fact that we're doing even this well is pretty good. Does that answer your question?
Well, I mean, are you going to discuss other astrophysical sources of electrons of comparable energy to dark matter annihilation?
Yes, tangentially. But if you have a specific question, I'd be happy
Well,
to
I'll hold
answer.
off then until
Okay.
we get into that.
Alrighty. So regions like this, where lots and lots of different emission mechanisms are piling up on top of each other, and the gas is commingling with the dust, are very complicated. And you can show that the spinning dust spectrum varies a little bit across the face of this thing, and it's very complicated. Down here, there's really not much going on. There's not a lot of dust. There's not a lot of H alpha. There's not a lot of sort of synchrotron down here. Well, there's not a lot of emission in the Haslam map. Let me put it that way. Okay, so this is the haze as a function of frequency at 23 gigahertz, 33 gigahertz, and 41 gigahertz. All right, and so here is the spectrum of that emission for our different CMB estimators. So the solid line here is the Haslam correlated synchrotron, while the dotted line is a 1 over R template that we're using to trace the haze and saying, okay, what's the spectrum of that 1 over R template? And now they're both normalized to be the same at 20 gigahertz. So you can see what's happening here with the CMB cross-correlation bias I was talking about before. So the spectrum of the CMB in intensity units goes something like this. So it becomes that bias becomes very important at high frequencies, and in fact the high frequency tail is moving around quite a bit. But in each case, the spectrum of the haze emission is harder than the spectrum of the Haslam correlated emission. And that's especially significant down here in the 20 to sort of 30 gigahertz range, where the CMB bias is sort of falling off. Oh, yes.
I guess under the assumption that the coefficients of the various foreground components are constant across the sky.
Yeah.
And as you map out, as you cut out more and more of the galaxy, you can be converging more and more to the. My question is, if you cut out more and more of the galaxy,
Yeah.
fit for those coefficients,
Yep.
and then using those fitted coefficients to subtract the foregrounds in the galaxy that you cut out, in the part of the galaxy you're cutting out.
Yeah.
Does the haze get bigger or smaller or no different?
So it's more or less, okay, so it's more or less no different as to what happens out here. What happens under this mask is very messy. And one of the reasons that this mask is on here is because the templates are completely failing. And you would expect them to in regions of high dust column density because H alpha is completely extincted. So the H alpha map is totally failing. The synchrotron spectrum goes wild down here because you're looking at supernova remnants. So sort of down here in the plane, lots and lots of crazy things are happening. So, but as you increase this mask away from here, this sort of blob remains the same. And you can show that it's there for much larger masks and much smaller masks as well.
So how do you define the mask?
So this mask is defined as one magnitude of extinction at H alpha. So dust column densities so that extinction at H alpha is one magnitude.
How big, so the most conservative mask on this plot would be roughly how big?
So you mean what is the angular size of this guy right here?
Or, I guess this is not the most conservative mask. The grayed out region there is not the most conservative mask. You were saying you could show that the spot's about the same, or much bigger or much smaller.
Sure. I mean, if you make a mask that completely masks out, this guy, that completely masks out from like here to here, you'll still see this excess residual up here and down here. Okay. Okay, so this ambiguity in the spectrum, so this will be eliminated with Planck. And the reason is because Planck's high frequency coverage, you can show that you can much more efficiently clean the CMB. So when you subtract it off the lower frequency bands, the spectrum should just be nailed down. So with Planck, we'll know exactly what the spectrum is. All right, so it looks like there's a separate hard synchrotron component towards the galactic center. Now, there are upcoming surveys at 5 gigahertz CBAS and 15 gigahertz QBAS, which Tony Reedhead at Caltech is starting up. And especially Planck, as I said before, will provide a lot more information on this. As we go down in frequency, where the lower frequency band should really nail down the spectrum so that we can then bring them up to higher bands. Okay. All right, so this is going to be a poor person's movie showing the statement that I just made that the synchrotron towards the center of the galaxy is harder than the synchrotron elsewhere. So this is the total galactic synchrotron at 23 gigahertz. So WMAP taking off dust correlated emission and H alpha correlated emission. And what I'm going to do is I'm going to step from 23 gigahertz to 41 gigahertz. And you'll see these synchrotron features like this big loop here, some of this region out here, and this region over here start to fade away much more slowly than this region, much more quickly than this region in here. So as you go from 23 to 33 to 41 gigahertz, you can see the morphology of this map is different, right? These big loop features. This is a much more centrally concentrated map than this big loop feature here. And then when you get down to 61 gigahertz, maybe you can convince yourself you still see a little residual, but you're starting to get dominated by noise. All right, so this is an RGB representation of that little movie. Yeah.
Could you just go back
Sure.
for a second? So you don't see anything at 94?
So at 94, you really start to get eaten up by the noise.
So at some level, this is a two-band?
No, I mean, you can definitely see, I don't have the picture showing just the haze at 60 gigahertz. So it's a detection at 23, 33, 41, 61, it's still there. By 94, this is statistically significant. And by 94, everything's kind of washed up in the noise.
And if you took the
So say this one, for example. So this dashed line, if you were to take this one and then extrapolate it, you would get roughly in the vicinity of what you're actually getting. So these are the template coefficients. Okay. So here the brightness corresponds to brightness, and the color corresponds to the spectral index that the emission has. This is in temperature units. If you want intensity, add 2. So, but this is the total synchrotron and just the haze towards the center of the galaxy. So the point is that the synchrotron up here and sort of around the plane here and also over on the side is much redder than the bluer part in here. Okay, so it looks like synchrotron, and the energy spectrum that you need to generate the synchrotron is something like e squared the NDE goes like e to the alpha, where alpha is somewhere between -0.1 and 0.2. So it's a hard E plus E minus spectrum, and it's extended emission. This isn't a point source, right? This is a huge area of the sky. This is out to about 30 degrees out here, and the sort of physical volume of it is roughly 4 kiloparsecs in radius. So it's a very large region with relatively smooth emission. So this is hard to produce astrophysically. We can talk more about that.
Total energy in these electrons.
The total energy in these electrons in what units? So it's roughly 10 to the 54, 55.
Really?
Yeah. So
I would do this myself if I got something a bit lower. I think, but I wasn't sure I got it correct.
okay.
Well,
Yep.
54 is a lot.
Yeah, it's very energetic. So Avery is not here. So one of the things we tried to do with Avery Broderick was create this guy with a gamma ray burst towards the galactic center. And if I'm remembering correctly, it had to be somewhere in the neighborhood of 10 to the 53, 10 to the 54. So yeah, there's a lot of energy. There's yeah, I'll leave it there.
Depends what magnitude you see.
Sure.
What's the cooling time for such a population?
So the cooling time, okay.
With the electrons.
So for an electron at 100 GeV, the cooling time to lose all of your energy is roughly 1 million years to somewhere between 1 million and 10 million years. And the path length to actually lose that energy is about a kiloparsec or so. It depends on your diffusion constant, but it's something like that.
You can argue it's difficult to actually get the electrons 4 kiloparsecs away from the center.
And keep them that hard. So you can get electrons away. You can get electrons away. It's just a matter of the cooling time, right? But the problem is that the energy loss goes like E squared. So if your initial injection spectrum is going to soften considerably as you get 4 kiloparsecs away from the galactic center.
What does polarization for you?
So polarization of this region is very tricky. Yeah, I have backup slides much later, which I could show you. But the polarization is tricky, and the reason is, so what you're alluding to is the fact that synchrotron is highly polarized, right? So, so you can easily show that if you take a model of the magnetic field of the galaxy that agrees with observations, and you add a few % turbulence in your magnetic field, then as you integrate 8.5 kiloparsecs in towards the galactic center, your polarization signal starts to go away. All right? It's actually it's the
You're saying it's not polarized. What we see is not polarized enough.
well, it's not significantly polarized, but the data is sort of not at the level right now where we can say. Right? And you see that in the polarization maps. When you look at the 23 gigahertz polarization map, and you look at the 23 gigahertz total temperature map, they don't look the same. You can see this big feature here, which is nearby. But then as you get down towards the galactic plane, they don't look at all like each other. Okay, so I will say that the synchrotron nature of this guy can be confirmed by Fermi. So these electrons, which are towards the center of the galaxy, will also inverse Compton scatter starlight photons. So electron comes in, hits a starlight photon, inverse Compton scatters it up to gamma ray energies. So then this is a process that would be happening sort of closer to the plane where the starlight density is sufficiently high. Okay. So obviously you knew where I was going with this, so now I will sort of go through the calculation to show that this haze is consistent with a sort of particle dark matter annihilation model. All right. So the idea is that WIMP annihilation produces energetic electrons, greater than 50 GeV and down in energy. It's halo annihilation. So towards the galactic center, it's extended injection. It's not point source injection. So can it explain the data towards the galactic south, which are these guys right here? All right. So in order to say, what sort of signal would you expect, you need some parameters. So you need your galaxy parameters. So we take the magnetic field, 10 microgauss, and diffusion constant, 10 to the 28. And you need some dark matter parameters. So we take a spherically symmetric halo profile, a WIMP mass in sort of the weak scale range, 100 to 800 GeV, sort of thermal relic annihilation cross-section, and several different annihilation channels. And then you need to solve the diffusion equation, which is this big monstrous guy right here, where K is the diffusion coefficient, B is the energy loss coefficient that goes like E squared, and Q is your source term. And then you want to find the steady state, and you assume isotropic diffusion. It simplifies.
Just a question, your injection is a delta function in energy or a distributed energy?
It depends. It's not a delta function in energy, but it depends on the different annihilation modes.
But it's not as flat as E squared ELD is constant.
No. It's not as, it is not as, so, okay, so when...
It would be more concentrated toward the mass of the annihilating particles.
Yeah, so we do consider annihilations that go straight to E plus E minus, which looks more like a delta function.
Yeah.
Right? But with these guys, as the particles cascade, the whole thing broadens, and you sort of go away from that delta function.
We've done this in the rental, you don't have to worry about branch alone.
Yes. Okay. So here is what the simple model gives you. So the solid line's an NFW profile. The dashed line is a slightly cusp r to the minus 1.2, which does a little bit better. The bottom line is for different disk heights. So you can see we're doing pretty well, actually, with sort of vanilla sort of models.
Are you fitting at different frequencies?
So this is just 23 gigahertz right now. This is different frequencies, but I'll get to that in 1 second. Okay, so r to the minus 1.2 is sort of looking more favorable. This is not in great contradiction with simulation. So if you were just to take a dark matter only simulation and say what is the index that we're looking at? So this is the region we're concerned with. So this is Via Lactea 2. This is Aquarius. These were from Mike Coulin and Carlos Frank. So the sort of index is looking something like a little bit steeper than NFW, a little bit cuspier. Okay. So on the right is the ratio of 22 to 33 gigahertz, and different particle annihilation models is a function of mass. Okay, so I think this is straight T plus E minus mu mu Z's W's. I'm not exactly sure. I don't remember off the top of my head. But the bottom line here is that multiple annihilation channels are consistent with the spectrum from 23 to 33 gigahertz. And on the bottom is the cross-section that we need as a function of mass for the different annihilation modes. All right, so then there's the prompt gamma rays, which I talked about before. So now this is for a specific annihilation to BB bar towards the galactic center. This is in a 0.1 degree little disk. So this is from a paper that we wrote with Dan Hooper, Zahar Hias, and Doug Finkbeiner. So this solid line is a point source that is located at the galactic center. And these different red, blue, and green lines are prompt gamma ray emission from BB bar annihilating 200, 500, and 1,000 TeV WIMPs. And now this guy is in, these curves are for a torus 0.3 to 0.5 degrees big. The point here is that as you go away from the galactic center, you're getting a more significant detection. So in these prompt gamma rays, these error bars are rough projections for Fermi. Prompt gamma rays may be observable by Fermi. Now it's worth pointing out that not all particle dark matter models predict prompt gamma ray annihilation, prompt gamma ray emission. You can construct a model relatively easy that gives you, very little prompt gamma ray emission. But all particle models, eventually, most particle models, nearly all particle models, wind up in E plus E minus. So the inverse Compton signal should be relatively robust. But I'll get to more of that in a second. All right, so I'm going to go away from microwaves now for a minute and start talking about cosmic rays. So,
well,
yes.
You didn't really give very detailed fits to the spectrum. You were comparing a couple of bands there, but you have more information, spectral information. And
you mean this guy right here?
Yeah, I mean,
sure.
You guys, have you fit all the different bands you have available to you, the spatial profiles?
So these are the two most constraining, and the reason why again is this CMB cross correlation bias, is because you're uncertain up to the spectrum of the CMB, you have a sufficiently broad range, right? When you just use the spectrum alone, these are the sorts of constraints you get. As you go to other bands, those constraints are going to broaden. Now with Planck data, these guys are going to get squeezed in quite a bit. And so with Planck data, we're going to start to cut out some of this region here and be able to maybe exclude models for certain masses.
But you were raising the issue earlier that cooling is going to affect the spectrum in the other parts. That would be true in almost any source model for the particle. And you get astrophysical sources like pulsars.
Sure.
They would tend to be constantly, maybe not too differently than dark matter collisions. And you'll know very well what the pulsar vertically in the practice evolution is.
Right. Sure, yeah. So the only statement... yeah, go ahead.
So you would expect to see in almost any model the effects of cooling on the spectrum.
Sure. Anything that injects particles is going to cool and soften the spectrum for sure. And so the only statement here is that towards the galactic center, there is harder synchrotron emission than elsewhere in the galaxy. And I'm not saying that this is evidence for dark matter annihilation at all. All I'm saying is that a particle dark matter model is consistent with the observations. Now, so the data is there. So then the question is, can you make a model of astrophysics that recreates the data? And that's basically the only statement.
And the cross section you need is the cross section that you need to get all of the point together in diagram.
Yes. So with this, with the semiana calculation and this idealized model of the galaxy, yes. Yes.
Do you assume the branching ratio in all the channels, or are they free parameters?
I'm sorry?
The branching ratio in the different channels, are these free parameters?
I am not 100% sure, but I don't believe the branching ratio is a free parameter. Can you calculate it from the data?
Like you have all these different channels, contribution from different channels. So how do you know the branching ratio for all these channels?
So these different channels, these are not data, these are models. So this is a specific particle model that goes straight to electrons and positrons. And then these are different models that go to different particles. But no, we can't constrain the branching ratio based on the microwave data. There are way too many other sort of parameters that go into it. Okay. So now I'll talk a little bit about cosmic rays. So this is the more controversial still. So there There are two experiments which have recently come out with some interesting data. Those are PAMELA, the payload for antimatter, and I forget the ELA, and ATIC, which is the Advanced Thin Ionization Calorimeter. PAMELA is a satellite. ATIC is a balloon experiment. This is ATIC after it crashed. This is ATIC before it went up. And so here's the data that has caused so much fuss. So this is the positron fraction. PAMELA has a big magnet in it, so it can tell the difference between positrons and electrons near Earth. And this is the ratio of the number of positrons to the total number of electrons and positrons as a function of energy. So from astrophysics, from straight acceleration, you might expect something just falling down like some kind of power law. But PAMELA sees this rise, indicating a source of injection of positrons. And assuming that positrons and electrons are being created by the same process, an injection of positron-electron pairs. All right, ATIC cannot tell the difference between electrons and positrons. It can only measure the total electron spectrum. It doesn't have a big magnet in it. But it goes up to higher energy. This guy cuts off at 100 GeV. This guy cuts off at a couple of TeV. So what ATIC sees, so this is what you might expect from just astrophysics, is the solid black line. The ATIC points are the red data points. And above about 100 GeV, there's this rise that then drops off around 800 or so GeV, and then falls beyond that. So potentially this could be pulsars. So this was a paper by Dan in 2008, shortly after the data came out, trying to explain the PAMELA data with a collection of unresolved pulsars and also two close pulsars nearby. This is still an open question, and there's lots of effort going into making the PAMELA spectrum with pulsars right now. But I won't say any more about pulsars at the moment. I'm sure I will be asked about them soon.
Well, I think the bottom line is that it's going to be very difficult to make any quantitative prediction for what the particles that can come out of a pulsar is in order to magnitude it works.
Yeah, I agree. I totally agree with that statement.
I mean, it really doesn't require any stretching at all.
Yep.
So the main question for you is, if you probably the answer is, can the annihilation rate locally be sufficient to explain both sets of data?
Sure. That's exactly what I'm going to answer. All right. So yeah. So pulsars are definitely something to consider here. All right. So to directly answer that question, so this is from Hollis and me and Neil Weiner and Lisa Goodenough and Doug late last year. So this is the PAMELA positron fraction for 3 different dark matter models ranging in mass from 150 up to a TeV. And this is the ATIC spectrum for the same parameters. So this drop-off here in ATIC is preferring a higher particle mass, right? Because for low particle mass, but you can't make more energetic electrons than the mass of your WIMP. So the 100 GeV models are not fitting too well, but up at the 1 TeV models are fitting better. So this is an annihilation mode which goes straight to electrons. All right, so now this is annihilation that's happening locally. Like I answered Wayne's question earlier, the sort of cooling distance is something like a kiloparsec for these very energetic electrons, right? So this is all annihilation that's happening locally, right? But I'm now going to tie this into the haze, which is 8.5 kiloparsecs away. Okay? So 8.5 kiloparsecs away, you have to extrapolate with some dark matter profile. We use an inosto profile, which is the profile I showed before that sort of went through the simulation data points. And for the same annihilation channels, for the same annihilation channel, you get out the haze emission. So how did we do the propagation through the galaxy? So this was not an idealized model of the galaxy. This was using GalProp, which is a cosmic ray propagation code where you can inject particles into a box and then propagate those throughout the galaxy. And there's some realistic estimates for the starlight radiation field, though there are still approximations that go into the whole thing. All right, so the thing to point out here is that for similar boost factors, we get the PAMELA positron fraction, the total electron spectrum from attic, and the haze from WMAP.
Okay, but in this calculation, how far are the electrons you see locally propagating from their source annihilation point?
So how far are these guys propagating from their annihilation point? Well, so the annihilation is sort of happening everywhere, right?
Sure.
Because we're annihilating it. There's a halo here, and the whole thing is annihilating, right? So some of them are very nearby, and some of them have diffused a little bit and lost energy.
What's the diffusion line locally? I mean, they're not coming from the galactic center out to us, right?
No, they're not coming from the galactic center out to us. So there's something like a 1 to 2 kiloparsec little region here that the electrons are probably coming from. Because, like I said, the 100 GeV electrons, so electrons in sort of this range lose their energy over a kiloparsec or so. So anything further away than about 2 kiloparsecs is all, will all be down here. So this is the inverse Compton. So given the haze signal, you can say, well, what is the inverse Compton signal towards the galactic center? And here are, for those 3 particle masses, here are the different inverse Compton signals you would expect. Where then here, this is just gamma ray emission from, so the primary source of gamma ray emission is cosmic ray protons crashing into the interstellar medium, making pi zeros, and those pi zeros decay and give you gamma rays. So that's this line right here. So these data points are egret data points. Fermi has released data up to about here, so all these guys are now down here and actually more in line with these others. This GeV excess, as it was known, no longer exists, which is a good thing. And so this is the inverse Compton sort of signal that you would expect to see towards the galactic center. This is averaged over a 5-degree radius towards the galactic center. So now here is the inverse Compton you would see for different models of the galactic parameters. So for different magnetic field, for different starlight radiation density, for different diffusion constant, for different diffusion index. Maybe you don't like Kolmogorov turbulence and you don't want the index to be 0.3 or whatever. So you can get a range of values. Specifically, as you dial up the starlight density field, you're losing energy preferentially to inverse Compton and not synchrotron emission. And so your total synchrotron goes down. But then to renormalize to the haze, your total gamma ray emission goes, sorry, I said that the other way. Yeah, your total gamma ray emission goes up. And vice versa, if you dial up the magnetic field, you get more synchrotron emission. And then when you renormalize to the haze, your gamma ray emission goes down, and that's that model on the bottom. So you can get a range of possibilities just from the galactic diffusion parameters. And so something we're looking into right now is, how well can we constrain the mass and cross-section, not just given the data points, but given realistic uncertainties in the galactic diffusion model. And that's something to consider.
The one prior that showed the egret data.
Yeah.
So can you just give an idea of where we expect Fermi's going to get to in terms of error bars?
The error bars for Fermi will be virtually unseeable down here, and they might get to be about, I'm thinking something like that big.
So the Fermi data set is clearly absolutely critical to this story. And will it be able, so will it be the best method in the near term to be able to nail this?
Okay, so there's 2 ways of, so I have a pessimistic and an optimistic answer. And the optimistic answer is, yes, Fermi is the best way to study signatures of dark matter annihilation. The pessimistic answer is that, so there's 2 ways of making gamma rays of dark matter annihilation. You make prompt gamma rays from the annihilation, or you make inverse Compton from the products, right? Lots of people are excited about pointing at subhalos or something like that and looking for diffuse gamma ray emission from subhalos. Which would be very exciting if seen. But not all, like I said, not all particle models give you prompt gamma ray annihilation. Prompt gamma ray emission, sorry. So then you're left with inverse Compton scattering. Inverse Compton scattering towards the galactic center would definitely be a smoking gun that this is synchrotron radiation towards the galactic center that we're seeing in the microwaves. Now, to the extent that that spectrum of the inverse Compton is consistent with a dark matter model, yes, this is the best way to constrain particle dark matter models. That said, if you can think of an astrophysical wave injecting E plus and E minus into the galactic center in sufficient quantities and with a sufficiently hard spectrum, then the data is what it is. At the end of the day, it's electrons towards the galactic center. So you can look at it either of those two ways. Jeff?
Can I ask the particle physics question? At least for the two sets of data on the left, there have been papers using annihilation to decay of dark matter.
Decay of dark, yeah, yes.
Does it matter for the right?
Does it matter for the right? So now, yes.
It's very natural, so that's why I'm asking the question.
Yes and no. So the decay in dark matter is a process that goes as density, not density squared, right?
Yeah.
So, so yes, it is harder to produce the haze in the galactic center because you need a little bit more of a cuspy profile to do that. But to the extent that you can create the haze signal, this is the inverse Compton signal you'll see. So if you can make a decaying dark matter model that fits the haze data, then this doesn't change at all.
But you're not going to fit Pamela at the same time, though.
You may or may not fit Pamela at the same time. If you have a model, so yeah, so okay. So if you're talking about Pamela and Attic and saying I'm fitting these guys and then going in towards the galactic center, to be honest, I'm not sure if the radial function of dark matter is such that you can also fit synchrotron.
It would be very surprising if you fit both this data with both a binary and a symbol decay model.
Yes.
But I have a simple question. How is it that you can get locally an e to the minus 3 decay particle spectrum, which is what that is?
Yeah, this guy right here, right?
And e to the minus 2 in the galactic center region, which is what you need for the haze spectrum.
So, okay, so this guy is, okay, so let's talk in E squared dNdE.
So that's EQ dN.
Right, right. So this is basically,
Flat and EQ dNdE, so e to the minus 3.
yes. So that's e to the minus 3. And so towards the galactic center, you're getting something like e to the minus 2, right? So the idea is that here's the signal locally.
Yeah.
And as you go towards the galactic center, where the dark matter density is going up, this thing is going up a lot. And so these electrons out here are going like that. As the whole as this bump increases, the electrons out here are steepening.
You're saying that there's this additional supernova component that is steeper than e to the minus 3. You're superimposing that on the spectrum that's harder than e to the minus 3. So it looks like e to the minus 3 here by coincidence.
It looks something like e to the minus 3 here. So yeah, so this is injection from supernovae, or some such things. And then this is the summation of that plus the dark matter is the different lines here. Now Pamela is, Pamela is tricky because much below this and you start to get into solar modulation effects. But yeah, so does that answer your question? So towards the galactic center, this signal right here is going to get a lot bigger as the dark matter density goes up. And that's going to
Well, it won't
harden your spectrum.
It won't change the spectrum unless there's additional component that applies in the local spectrum, which there probably is.
Yes. Well, it won't change the spectrum of... So the electrons in the galactic center...
I mean, the rate at which you're producing them is presumably independent. It's decoupled from the spectrum,
Yes.
unless there's additional component.
Yes. Okay. So this is just the conclusions. So there's these excess microwaves towards the galactic center, which are consistent with synchrotron radiation from a hard spectrum. Cosmic ray population, something like E squared dNdE goes like e to the minus 0.1, 0.2. A simple WIMP model and a simple galaxy model fits the data reasonably well. with the appropriate cross-section and density profile and mass, and particle dark matter models, which reproduce the haze, naturally explain the local positron and electron populations when you use some particle propagation code like alprop and vice versa. So here's where we are right now. We have these three very nice data sets that we are interpreting in various different ways. Positron fraction from Pamela, total electron spectrum from Attic, anomalously hard synchrotron towards the galactic center from WMAP. And in the future, we have Fermi and we have Planck, which are going to be our two main ways of approaching this issue. And who knows what they'll see, but the things to look for are inverse Compton gammas from the E plus and E minus from these guys, possibly prompt gammas depending on the different particle model. And then Planck, because it's going to be able to create a very clean CMB map, will reduce the uncertainties in the spectrum of the haze, and maybe we'll start to be able to constrain some particle models using the spectrum in the low frequency bands. And I'll stop there.
You didn't say anything more about spinning dust.
I didn't say anything more about spinning dust.
Change the magnetic field, for example, in the galactic center region. I mean, how much uncertainty does that introduce?
So when you change the magnetic field, you get more emission, right? But you don't really get much harder emission. You don't change the spectral hardness very much, right? So, it is often said by me as well that, this is excess microwaves towards the galactic center. That's actually kind of a misnomer. It's anomalously hard microwaves towards the galactic center. So changing the magnetic field will give you more overall emission, but you have to make a harder spectrum so that you don't see this at lower frequencies, right? So that's how the I could draw it up here. The plot the cartoon I had at the beginning was, so this is 20 to 100, and then down here at 0.4. So we have a map down here, and we have 5 maps up here. So if you were to just have, so say you took this guy like this, if you were to just increase the magnetic field strength here, you would get brighter emission at 20 gigahertz, but you would have the same spectrum, so you would expect to see it down at 408 megahertz. So the only way to have it be here but not here is to make the spectrum steeper, is to make the spectrum flatter, which you can't do with the magnetic field, more or less.
So can you specify a bit like the assumption you do related to the variation of the spectrum? Do you assume it's constant, or you said you consider various areas?
Yeah, so let me refer to this plot. So when doing the residual and making this guy, we assume that it's constant across the sky insofar as we just fit the Haslam template to the sky. And we see this. Now, when we let the spectral index vary,
so the fact that it doesn't depend on the cut, you said on mid-map, right? Because that all the whites come from there.
the fact that it doesn't depend on the cut. Yes, that's right.
It's natural, right?
So now this guy is fitting in different regions of the sky. So this guy is broken up into smaller regions. So, and the spectral index variation, so, it's very hard to measure the spectral index variation because you have other things like spinning dust in the way. So once you get rid of that morphologically, this is really the way to display spectral index variation. So if you're asking what is the spectral index variation of synchrotron in the galaxy, it looks like that, where this is the spectral index, +2 if you want to go to INU. So if you were to let the spectral index be a free parameter, then this is what you would get for your answer as a function of pixel. Right.
Okay, Greg is only here today if you want to talk to him, so let's thank him.